And now we are finally down to our last topic on multiplication of vectors. So in the multiplication of vectors, we have actually two types. So the first type of vector multiplication is the scalar product, also called the dot product. And the second is your vector product, which is also called your dot product. So the names of this vector is actually very significant for us to remember everything. So the scalar product, its result is a scalar quantity, meaning you just have a single number from the scalar product of your two vectors. Okay. This is also called the dot product because of its symbol. Say, for example, you have two vectors A and B, and you want to get the scalar product or the dot product of these two vectors. You're going to write this one as your A dot B. Okay. So this one here is a dot. Okay, that is why your scalar product is also called a dot product because of the symbol, the dot. Next, your vector product. So the result of your vector product is a vector quantity. So it's just easy to remember. Now your cross product, your vector product is also called a cross product because again of the symbol. Again, suppose you have your two vectors A and B. So writing the dot product is like this. So you have your vector A cross with your vector B. So you have here your cross multiplication symbol or your cross product. So again, your scalar product or your dot product has a scalar quantity for the result, and your vector product or your cross product has a vector quantity for the result. Let's go into deeper of this multiplication of vectors individually. So we start first with your scalar product. So again, the scalar product, also called the dot product of vectors, this is given by your a dot b. Okay, your a dot b is equal to your ab cosine phi. Okay, so why is it that it is like this? Now let us go into this figure. So suppose you have your two vectors here. You have your vector a and then your vector b. So first, to demonstrate your dot product, replace the two vectors tail to tail, just like this one. And the angle between the two vectors, which is this one here, this smallest angle between the two vectors is phi. Suppose that is phi. Okay. Your dot product is like this. So your a dot b, which is equal to ab cosine phi, happens to be that way because what the dot product do is for a dot b, we project your vector b here. We project your vector b onto your vector y. So if you're going to project that one, so we have here the projection, and you know that that projection is just your b cosine phi. Okay, since this side here is adjacent to your angle phi, so that is your b cosine phi. So your a dot b is actually equal to the projection of b into your vector a. So your a dot b is equal to your ab cosine phi. Okay, your a dot b is also equal to, if you're going to project your vector a into your vector b, like this one here. Okay, so we have here your vector a, and then we project this one onto the axis of b. So we have this projection here, Okay, this is just opposite your this is just adjacent to your angle phi. This is equal to a cosine phi. So your a dot b is also equal to the projection of a to your vector b. Um, if the angle P is between 0 and 90 degrees, your A dot B is positive. If P is between 90 degrees and 180 degrees, okay, your A dot B is a negative. And if your angle phi is equal to 90 degrees, or when your two vectors are perpendicular to each other, this is, or your scalar product is equal to 0. Later in the course, we will use this concept of your scalar product in our understanding of the concept of work. Okay. Now, what are the dot products of your unit vectors? So again, our unit vectors are I hat, j hat, and k hat. And let me just redraw your unit vectors, the XYZ plane. So you have your I hat, j hat, and k hat. Okay. And again, these three vectors here are orthogonal or at 90 degrees with each other. So suppose you want to find the dot product of vectors pointing in the same direction. Like say for example I hat dot I hat, or j hat dot j hat, and k hat dot k hat. This is just equal to 1. And why is that so? Remember again that your unit vectors are vectors of unit or of magnitude 1. So if you have a dot b cosine phi as the dot product of your vectors, so since your unit vector has magnitude 1, so this is just 1 times 1 cosine phi. Now, what is phi? Okay, if this is your I hat and you dot it with another I hat, okay, your second I hat just points in the same direction. Okay, so if this is the case, the angle phi between your two vectors is equal to 0. And what is cosine 0? So cosine 0 is just equal to 1. So that means your um, the dot product of your I hat that I hat is equal to 1. So you have 1 times 1 cosine 0. Cosine 0 is 1. So that is equal to 1. On the other hand, if we look for the dot product of your vectors which are at 90 degrees with each other, like say for example your I hat dot j hat, your I hat dot k hat, and your j hat dot k hat, this is equal to 0. And why is that? So again, your unit vectors all has magnitude of 1, then cosine phi. If we take, for example, your I hat, that j hat, remember here that they are orthogonal, so they are at 90 degrees. And we have your phi is equal to 90. So you have cosine 90. And what is cosine 90? This is just 0. So getting the dot product of your unit vectors that are orthogonal to each other, the dot product is always equal to 0, as they are again at 90 degrees with each other. Okay, so using the component form with the vectors, if again say for example your vector A is equal to ax I hat plus ayj hat plus azk hat, and then your vector B is bx I hat plus byj hat plus bzk hat, your A dot B is just equal to axbx plus ayby plus azbz. Okay, so you just multiply um, magnitude of your vectors, data components, the components of your vectors pointing in the same direction. So these are all your x components, your y components, and then your z components. The proof of this one will be left as an assignment for you. Let us have an example of calculating the scalar product. So we have the formulas here. You have your a dot b is equal to ab cosine phi, or you have your a dot b is equal to ax bx plus ay by plus az bz. Okay. So find the scalar product a dot b of two vectors shown in the figure. The magnitudes of the vectors are a is equal to 4 and b is equal to 5. So your first vector a is here, and this is pointed 53 degrees north of west, and your vector b is here, and uh, this is at 130 degrees measured from the positive x-axis. So again, the first vector a is at 53 degrees from the positive x-axis, and your vector b is at 130 degrees from the positive x-axis. The magnitude of a is 4 and the magnitude of b is 5. So in finding the scalar product of these two vectors a dot b, so your a dot b, you can either use this formula here, or you can also use this one here. If you're going to use this one, this is just straightforward. Whereas if you're going to use this one, you still need to find for the x and y components of your vectors. So let us just use this first formula here. So your a dot b is equal to ab cosine phi. So the magnitude of your vector a, again, is 4. And then for your vector b, you have 5. So you have cosine phi. Now what is cosine phi? Again, your phi is the angle between your two vectors. This is the smallest angle between your two vectors. And for this case here, your angle phi is this one here. Okay. Again, this is the smallest angle between your two vectors. And for this example, your angle phi is here. So your angle phi is equal to 130 degrees minus 53 degrees. This is equal to 77 degrees. So you have cosine 77. Therefore, your a dot b is equal to 4 times 5 times cosine times cosine 77. So your a dot b is equal to 4.50. You should also be getting the same answer even if you're going to use this formula here. Okay, you're going to use that formula. You find the x and y components. So we project first your a onto the x and then your a onto the y. The same case here. Project your b onto the x-axis and then project your b on the y-axis. Multiply the ax and bx components. Then you add it with your ay by components. You can check it yourself to see if indeed the answer is still 4.50 even if you're going to use this other formula here. Let us have another example of your scalar product, but this time this is about finding the angle between two vectors. So find the angle between the two vectors a of 2i hat plus 3j hat plus 1k hat and b of negative 4i hat plus 2j hat minus 1k hat. If you're going to draw your vectors in the xyz plane, this is how it will look like. So you have here your vector a and then your vector b. And our target here is to find the angle between the two vectors, which is this angle here. And we call this angle as your angle phi. Now, what is this angle? Okay, recall that we have two formulas on the previous slides. So to find for your vector product, you have your vector A dot B is equal to AB cosine B, and the other is you have your A dot B is equal to AX BX plus AY BY plus AZ BZ. Okay, so in order to find your angle P here, we can actually equate these two equations. Okay, equating these two equations, equating, you have your AB cosine phi, which is equal to AX BX plus AY BY plus AZ BZ. Okay, and we only wanted to solve for your phi, so we have here your cosine phi, which is equal to AX BX plus AY BY plus AZ BZ, and this is divided over by the magnitude of A times the magnitude of V. Okay, let us not go into more detail, but your AXBX plus AYBY plus AZBZ is equal to -3. Okay, please check it yourself. And the magnitude of A is square root of 4, square root of 14, and the magnitude of B is square root of 21. So this is your cosine phi here. And to get for your phi, we just get the cosine inverse of your -3 divided by your square root of 14. That's your square root of 21. And you get your phi, which is equal to 100 degrees. Okay, to save time, please check this yourself.